Hey guys, welcome back to the dynamics video series for your course. And this one's video is going to be mainly about pulleys and how to solve pulley problems that don't require free body diagrams. So let's go ahead and get started with this first problem I made, just like an intro to how we should think about these through. So the problem states that block A is being pulled down with a constant speed of 3. And then what's the speed and direction that block B is moving, right? So I've labeled block A over here and block B over here. Okay, so we're gonna have to figure out essentially. I know I said it at the beginning of the video, kind of explicitly, that you don't need a free body diagram, but during an exam, you actually won't know. It won't be directly stated to you if you need one or not. So it's important to know how to figure these things out. So firstly, we're gonna try taking out our free body diagram, right? So do we need one? Is it a dead giveaway? The problem. So if it's a dead giveaway, the problem would be something like give me this force, right? If it's asking for a force, that's a dead giveaway that you need a free body diagram. But this question isn't asking us for force. It's asking us for two things, speed and direction of this block B block, right? So to figure that out, we have to actually count our degrees of freedom, right? So DOF. You guys should be a little accustomed to this by now. So let's look at this. I'm gonna what's the word? Before I start, I'm gonna set up an axis system just to make it easier in my head, right? So we'll just try going up as positive and going to the right as also positive, right? And then negative for left and negative for downwards. So as block B or block A moves, what else moves, right? This pulley doesn't move, right? Because it's locked in place with this bar. This pulley probably does move, right? Because there's nothing locking it in place. And then this pulley also moves alongside block B, right? So can you imagine, right, if you stop the motion completely of block A, right, so it's locked in place, can anything else move? Just think for a second. After a second, you should see the answer is no. If the block B is not moving, block A is not moving, these chords are incompressible and don't extend, then nothing else can move. So our degrees of freedom, right, we just stopped one thing to make the whole system stop moving, is just going to be equal to 1, right? And so what we know with 1 degree of freedom is that we're given 1 acceleration, we can find any acceleration. If we're given 1 velocity, we can find any other velocity in the system, right? So let's see what we're given. We're given a speed and a direction, right? 3 and downwards. And we're also given to look for a speed and a direction. So this is possible, right? So we know we're not going near the free body diagram. We have 1 degree of freedom, and we can solve it straight away. So let's actually get into the problem and how you're going to solve it. So let me erase most of these arrows since they're kind of useless now. So kind of the first step when you're solving these pulley problems is you want to label everything that moves, right? So everything that's moving, block A is labeled, block B is labeled, that things are moving. But what else is moving, right? Giving those things labels is going to help us out later when we start writing our equations. So this pulley is not moving, right? We said already that's fixed to that ceiling up there. This block isn't tied to anything fixed, right? So this thing will probably be moving. So let's label it preemptively as A and B are taken, so C. And then this pulley is also moving, right? So you're preemptively thinking, oh, let's label it D. But if you notice something, block A, or not, sorry, block A, block B and this pulley are always going to have the same movement, right? Because they're fixed to each other with this bracket or this cord or whatever you want to think about it as. So they're always going to have the same movement. So we can actually just treat this whole thing as block B, right? So we don't need to label this pulley. And where my arrow is going. Oops. So, knowing that this thing was labeled C, we have all our things labeled, right? And we're going to start working with rope equations. Right? So, we're going to want to getting first the length of both chords. So the length of, I already color coded them for you. It may not be on an exam, but usually Dr. Everett's nice with it and they'll color code it. The length of the blue chord and the length of the red chord, right? Expressed in different ways. So we're not given actual distances. So to find the chords, we're just going to use arbitrary distances from kind of a measuring point. So let's treat the measuring point as the ceiling, because I think that's an easy fixed location we can measure from. And then let's get the distances to each of our objects that are moving, right? So the distance from the ceiling to this block A, right, is going to be YA, just to give it a name. And the distance from the ceiling to this block C, or not this block, this pulley C, we can just write it as YC, and then the distance from the ceiling to this pulley that's connected to block B, we can just treat it as, or label it as YB. Okay, so now let's get the length of this blue cord. So I'm going to use a highlighter so that we can see me as I'm going. So this section of rope, right, over here on the left side of this pulley, what is that length, right? It ends at YC, right, or not YC, YA, the length there at the end. But there's some distance here above it that we don't have an exact measurement for. And if you notice that that distance is just the same as this right here, right? And that is never changing because that pulley is fixed to the roof at that point. So we can actually just treat this, what's it called, segment, as a constant value, or a constant one, let's just call it. So that length of this first rope, or this side, is just going to be YA minus that constant value, right? And that's that first length. If we go to the right side now, we want to get the length of, back to the highlighter, this side, oh, not red, this side, right? It's kind of the same idea. It's this length YC because it meets the C down here, but there's also a constant up here, a not changing fixed distance value that can help us figure out what this should be labeled as, right? And if you notice, it's the same thing kind of, but now we're using YC. So plus YC minus C1, right? Because if we get this whole YC distance and subtracts this C1 value, we'll get the distance of this measurement of rope, right? And then lastly, I hope you notice this, this right side is just going to be equal to the length YC, right? So plus YC. Okay, so that's the length of the blue rope, because now we're done there. So the length of the red rope, we can figure that out as well. So what should this right side be equal to? Or not right side, left side be equal to? If you notice, it ends at YB, right? It's got that little line there. And it starts at YC. So if it starts and ends at YB and YC respectively, we can just label it, that first part, as YB minus YC. Perfect. And we can keep going. So plus, and then the length of this right side, right, I'll highlight it again, is just going to be, I hope you can notice that, YB. Okay, so we have these two equations for the length of the blue rope and the length of the red rope. Let's try and finish up. So now we're going to use a strategy that can relate these YB, YC, YA values to the velocity of their respective blocks and pulleys, right? So what we want to do is we want to get the length of the blue and the length of the red and take their time derivatives, right? What that's going to do, right? Oh, these are equal signs, right? For length of blue and length of red. What that's going to do is tell us how these YA, YC, YB values are changing as a block is moving, right? So let's just take the derivative. So of the first one first, so block B, or the blue line. So YA is just going to become YA dot. And then any constant, when you take the derivative of it, is still, what's it called? It's not changing, right? It's a constant. So a derivative measures change. So it just becomes 0. So we're actually just going to get rid of any C values that we wrote in. So this is going to be YA plus, and then that YC dot, right? From that next YC, and then plus YC dot again, right? And then we can change this over to the length, or the length of blue dot equals 2 YC dot plus YA dot. And then we can notice one other thing. So with these derivatives, we said that constants don't change, right? So the derivative is 0. And the length of the blue cord, right? We already said that these cords were incompressible and they're not going to extend, right? So the length of the blue cord is actually also unchanging. So this LB value is just 0, right? So we can actually write this again as 0 equals 2 YC dot plus, let me write that a little better, YC dot plus YA dots, right? And then let's do the same thing for the red cord. So the length of the red cord, right, the first time derivative, that's what that dot means. It's just going to be equal to YB dot minus YC dot plus YB dot. All right, and then we can do that same extrapolation where the length of this red chord, the change in it, is going to equal to 2 times YB dot minus YC dot, right? And the last thing, where the length of the chord never changes, so we get that 0 equals 2 YB dot minus YC dot. All right, and then let's take a look at these two equations, right? So these two equations are actually what we can use to solve. First thing, we're gonna try and get them to be equal to each other. So they do have a common term, which is YC, right? So let's evaluate both of these equations for YC. So I'm gonna just drag these to the bottom. Let me grab them, drag them over here. So this first equation, right? If you notice, we can just move the YA to the other side, right? So this becomes negative YA, right, equals 2YC. And then we can just divide by 2 to get this YC on its own. So this will become that negative 1/2 YA dot, sorry, I'm forgetting these dots, equals YC dot. Perfect. And then same thing for this equation. Let's solve for YC in it. So this one's a little easier. We can just move YC to the other side, and we get that YC dot equals 2 YB dot. Perfect. And so now, since each of the equations, this side is equal to YC and this side is equal to YC dot, we can just equate the other side to each other. So these two will become that 2 YB dot is the same thing as negative 1/2 YA dot, right? And then we're not fully out of the woods yet. I need to make myself a little bit of room here, so I'm going to slide all this stuff over. So YB dot and YA dot are not exactly connected to the velocities of YA and YB, or the blocks of A and B. And that's because we created these axes at the beginning, right? So as YA, right, is getting bigger, as this value, right, from the roof is getting bigger, how is block A moving? Block A has to be moving downwards as YA gets bigger, right? So they're not exactly related, right? If YA is getting bigger, then the velocity of VA is negative, right? Because it's moving downwards. So we're going to evaluate that here, that YA dot equals negative VA. All right. And what about block B? So as YB gets bigger, right, as that distance gets bigger, that's what we're talking about with the YB dot, that'll be the positive value. The velocity of B is actually negative, right, because it's moving downward based on our axis, right? So it's the same thing here, where YB dot equals negative VB. So let's go ahead and write an equation where these two equal each other, right? So we know that, what's it called? Y, or 1/2 YA dot is equal to 2 YB dot, right? And then based on what we wrote up here, we know that VA is -3 because it's moving downwards, right? And we're given the speed is 3. And we know that VB, right, is going to be equal to negative YB dot, because as YB is getting bigger, the velocity of B has to be going downwards, right? So which we associated that with a negative value based on our axis. So this will actually become that negative 1/2, right? Negative VA is equal to, all these negative values are gonna trip me up, equal to 2, and then YB dot, which is negative VB, right? And then let's rearrange this equation real quick to solve for VB. So VB, I'm gonna just write it up here, just to give myself some room. VB is equal to, what would it be equal to? I think it's negative here, 1/4 VA. I think that's correct. Yeah, it should be. All right, and then now we can just plug in our given VA value. So VB is equal to negative 1/4, and our given VA value was 3, right? But we know it's going downwards, so it's a negative 3. That's what we got. So we'll put negative 3 in here. Right? And these two negatives will cancel out, and we'll get that our final answer of VB equaling to 3 over 4, or 0.75. And that'll be the answer for the first question. So it's a little confusing. But make sure that you start off by figuring out if you need a free body diagram, writing your length equations correctly, right? So figuring out what's moving, labeling it. If there's stuff that you that's labeled that's not moving, like let's say this top pulley up here was labeled, I don't know, E, right? We would get rid of this label, right? Because that would just confuse us. We don't need a YE because that would be a constant number. And then just making sure we take the derivatives correctly, and then relating these velocities to the YAs and YBs properly, right? Because if something's moving down, even if the YA is getting bigger, the VA is negative for our axis that we set up. So that's the answer to this problem. All right, here's the second problem. It's a little more complex than the last one we just did, so you might think it's going to be a little confusing. You might be overwhelmed at this point. But it's important to just go step by step and try and just retrace the steps we did last time. So let's start off by reading it. So in the rope pulley diagram, C, D, E, and G are fixed. Point H is pulled to the right 2 meters per second. The angle theta is 30 degrees. What's the speed of B, and what direction is it moving? So it looks confusing, but let's just take it step by step. So let's think about, do we need a free body diagram to solve this problem? Right. So what do we need to know if we need a free body diagram? Is it a dead giveaway? Is it asking for a force? No, it's asking for a speed. It's asking for a direction, right? So that's fine. Not a dead giveaway. So what's next? We're going to have to count up our degrees of freedom. Right? So as, let's say, something is moving, let's say this H is moving, can anything else move, right? G is locked in place. A can move, right, because it's on this slope. It said C was locked in place, D is locked in place. This pulley can move, right, because it's not locked in place. E is locked in place, F is locked in place, but B is also moving, right? So we kind of have 4 things moving in this case. We have H, A, this pulley over here. Let's just call it pulley for now, and then B. Right, so let's think about it. If H is able to stop moving, right, or we're able to hold H in place, right, can anything else move? Think about it for a second. The answer is no, because this cord, right, connected to A, won't allow A to go any direction, right? So all the cords stop moving, and if all the cords stop moving, everything is locked in place, right? So this problem is only going to have 1 degree of freedom. So I'm going to erase all these marks. All right, so 1 degree of freedom. We're given 1 motion, right? So we should be able to find 1 other motion, right? Specifically, we're given a velocity, so we'll both be able to find 1 other velocity, or just the velocity of B that this question is asking for. All right, so let's make our first step simple. So let's label what H is doing. So H is going to the right here at 2 meters per second. What is it, 2? Yeah, 2 meters per second. All right. And then let's set some axis, right? So let's say, oops, that going to the up and down, right? Going up is positive, and then right is also positive, right? So that's just so we can have our velocity axis going. Okay, so what's our step here? We want to create some rope equations or some lengths equations for these ropes, right? But let's check out how many ropes we actually have. So based on the coloring, it looks like we have 3 different ropes, right? We have this first red rope, we have this second red rope, and then we have this third blue rope, right? So that would be the case, right, if we need a free body diagram, if this A was somehow contributing, right? But if you notice, right, does the system actually change, right, if A just disappears and becomes a rope like this? Well, no, not really, because all A's point here is to connect that first red rope and that second blue rope, right? So if A disappears and there's still a rope there, it's an identical situation, right? Because A isn't influencing the speed of H or the direction of H or the speed of B or the direction of B. So we can actually kind of just treat A as not existing, right? So I'm just going to color over it with white. We can treat it as though it doesn't exist, right? So we can treat this first rope, right, the first red rope and the blue rope, as one continuous rope. And then the second rope would be this red one over here at the bottom right. All right, so that's a good simplification. That helps us a lot. This angle is, I'll label it just because it says it, but 30 degrees. It doesn't matter explicitly too much because, again, we're not using A value, so there's not going to be any forces at A. But we'll continue on. So our next step here for our rope equations is to start getting distances from these fixed points like we did in the last problem. So let's see. So let's treat this as some distance, right? If you notice, this H point and this, what's it called, circle, are both moving, and they're both moving at the same motion, right? So we can treat them as the same body. So I'm just going to go ahead and treat it as H, or both of them as H. So I'm just going to go here, and this will be the X of H. All right. Before we do that, actually, it's a little confusing if we have all these letters around here, because you start thinking, should I get X of C, X of B, X of G, X of F, X of E? So let's go ahead and get rid of the letter or marking on anything that is not going to be moving. So the question explicitly stated that C, D, E, and G are fixed points, right? So let's go ahead and get rid of all of them. So I'm going to get rid of G, get rid of C, get rid of D, and get rid of E, right? Because those are all fixed, right? So there's no point in getting a distance to them. It's just going to be a constant every time, and when we do our derivative later, they're just going to disappear, right? So let's keep going. So now we have this XH distance. Let's get this distance for B. If you notice, F and B are going to have the same motion, so we can actually erase F and just treat this whole thing as B. So let's say this distance from this fixed, what's it called, section right here, this means fixed, right, is going to be some distance, we'll just do it there, XB, right? And then there's one more, right? So there's only one more thing that's going to move, and that's this pulley right here, right? So we can create a distance there. Let's give it a label. Let's call it C, just because that's the next letter. So we have HBC. So then this distance is going to be, we can treat it as, I like using X for anything that's not up and down. For this one, we can use Y, just because it's up and down. So Y of C, right? So that vertical distance. All right, so then let's start creating our rope equations. So the first one is going to be this first rope. I'm just going to call this one rope 1, just because the color is a little mixed. And then this one will be rope 2. Right? So rope 1. So the length of rope 1 is going to be equal to, right? So let's get the length here. So what is, get my highlighter out again, this first distance. If you notice, it's just XH. So we can just write XH, right? Plus, and let's figure out this distance. So highlighter, I always forget what the highlighter is. This distance, it's XH, right? Because it has this portion right here. But XH plus whatever this is, right? So this point is fixed, and this point is fixed, right? So if you notice, this one is never going to change. So it's just a constant. So I'm just going to label it C1, just because there's going to be a lot of constants in this one. So that one will be C1. So that second half of the rope, or that second half of the rope that's attached to the H block, is going to be XH plus C1, right? And then let's keep going. So we can notice a couple other things. It gets a little simpler here. This entire length is between two fixed points, so this is also just a constant. So let's just call it C2. Same thing with this length over here, right? It's just between two fixed points, so C3. And then this length down here, right? Well, let me add C2 and C3 first. There we go. And then this length down here, let's try and figure out what this is. So this is between a fixed point and something that is moving, which is C. So it's not exactly, we can't just call the whole thing a constant. So it's YC, which is this portion, right? This down. And this top portion, right, is going to be the distance from this fixed point to this fixed point, right? So over here, which is, again, just a constant between two fixed points that won't change. So that's going to be C, what am I on? 3, 4. So this is going to be, this vertical side of this right side is going to be YC plus C4. So plus YC plus C4. Right? And then we have this final distance for this first rope on this side, right? And that's just going to be YC. So plus YC. Simple enough. Let's get the rope equation for rope 2. So that's going to be a little bit of a shorter rope. So let's see what it is. This first distance, right? It's a little confusing at first because there's not exactly anything we have done with it yet. If you notice, let's see. So this distance right here is a fixed point, right? And this thing is moving. If we can call this distance YC, right? This distance that we labeled as YC, right? This fixed point can be related with this fixed point up here. Or let me use a different color so it's explicit. So this fixed point up here and this fixed point down here can be connected, right? So this is a constant value. This is never going to change because these 2 points are fixed, right? But this YC that's inside it is changing, right? So we can just treat this as this arbitrary constant that we created, Y, oh, no, sorry, Y, C, what are we on? C5, what's it called? Minus YC is going to be just whatever this portion is, right? Because YC is going to be a portion of this entire constant. So C5, or for the second equation, C5 minus YC is going to be that first part. And then we can do the second part, right, which is this bottom portion, right? And that's just going to be, we can do as the XB. Or we can treat XB if we wanted. Let's actually move XB, because this point down here, just to make it a little easier, is also a fixed point, right? So let's treat XB as this, because we just need a fixed point to treat it from. So this can be XB. And we'll treat this just whole thing as a fixed point. Right? So plus XB. And then this top portion, right? We can label that as, again, like we did with the last one, where, what's it called? This distance from this fixed point, let me use a different color now. This green distance, right, is always fixed. So we can treat that as C6. And it's this going to be XB minus C6 is going to be this top portion. So let's do that. So this now it's plus XB minus C6. All right, so there's a lot of constants in this one, which is fine. We actually don't care how many constants we add because we're going to take a derivative and constants disappear either way. So let's go ahead and do that. So let's take the time derivative of L1. So L1 dot equals 2. Just write it across. XH dot plus XH dot. That constant 1 disappears. The constant 2 disappears. Constant 3 disappears. Plus YC dot. And then constant 4 disappears. And then plus YC dot again. Right? So after all, this becomes 2XH dot plus 2YC dot. Right? And that equals 2, 0. Because the constant, well, sorry, not the constant, the length of the chord is constant of chord 1, rope 1. So if we take the derivative with respect to time, it's a constant value. So it's just going to be equal to 0. So this is the first equation we're going to use. Let's take the length, the time derivative of the second length. So let's see what that is. So it's just C5 is a constant, so that disappears. So we have negative YC dot plus XB dot plus XB dot again, and minus C6, which just becomes a 0 after a constant. So this becomes 2, oh, that 2 looks funky, 2XB dot minus YC dot equals 0. All right, if you notice, we have YC in both of these equations, so we can actually do something to relate them. So let's solve both of these equations for YC. This first equation, B is going to be over here. So if we move YC to one side, we have negative 2YC equals 2XH. These are all dot terms, sorry. And then if we want YC by itself, then this becomes, we divide both sides by negative 2. YC dot equals negative XH dot. Perfect. And then for that second equation, let's go ahead and do it just right below it. Oh, that looks dumb. Let's go ahead and do it just right below it. So if we want to solve for YC, we're just going to move it to the other side. And so YC dot equals 2XB dot. Cool. So now we have two equations for YC, right, for what they equal to. So we can just equate the other side of both of these equations, and we'll get something else. I'm going to write it over here. Right? So negative XH dot equals 2xb dot. So now we have an equation that relates, relates h and b, which is what we're talking about because we're given a motion for h and we want to find the motion of b. So let's convert these into their velocities. So as xh, right, gets bigger, as this value gets bigger, h is moving to the right, which is positive, right? So we know that xh dot equals vh, right? Just straight up, no negatives because they're increasing in the same direction. And then for the b, just based on the same principle, right? If b is moving to the right, then xb is increasing. So this is also the case. So xb dot equals velocity of b. There's no negative value because they're increasing in the same direction. So let's replace those values really quick. So negative vh equals 2vb, right? And then now if we want to find the velocity of b, we can just plug in our velocity of h right now. So let's plug that in. So negative, and then the given velocity of h was 2. 2 to the right is a positive 2. So negative 2 equals 2vb. And then we can solve for vb here. And then vb, our final answer, is just going to be equal to negative 2 divided by 2, or just negative 1 meters per second. What does that mean? That means that as h gets pulled to the right, b is going to be moving at 1 meter per second to the left. All right. And let's see if that makes sense. Is there a way it could be moving to the right? Not really, because the b is locked in place, and as that cord gets pulled up, the b is going to be pulled to the left. So I think it makes sense in my head. So I think this is the correct answer. And that's going to be the end of this video.